In this video, we're going to look at properties of integrals, and we're going to tie that back to the summation version of the integrals themselves to give some intuition around how we can manipulate or handle or transform an integral that we're given. There's a long list of basic properties that we can imagine for integrals, and some of them are relatively straightforward if we bring it back to area ideas. We won't look at all of these, but they're all fairly intuitive, typically with a sketch or a return to the sum notation. For instance, if we're asking for the integral from a to b of some function with respect to x, but the a and b are the same value, then if you think about the area interpretation of that, where a and b are at the same point, then what is the area underneath that graph at a single point? Well, the area is going to equal 0 because there's no width. And if there's no width, then there's no area. And so we get that result that this integral, if the starting and end points are the same, we'll get an integral value of 0. Also related would be this one here, where if we're integrating simply a constant, then if we think about where we started with our integrals and a constant velocity, and we integrate that from a to b, then we're simply talking about the area of a rectangle, which is b minus a in width and c in height. And so we get the integral value is quite simple for that particular example. This one here at the top talks about the effect of reversing the direction of the limits of integration. And all we do there is if we swap these, it's like changing the direction of the integrals. Instead of integrating from left to right, we're integrating from right to left. Well, that ends up changing the sign, as it turns out, of the delta x terms. So to counterbalance that, we include a negative sign. All of the other formulas here are typically rooted back to the summation notation, and imagining if we take a constant times each individual value, well, it's the same as taking a constant times the area of the original function, under the original function. And so we can change the order of the operations of multiplication, or here of addition. This last one's interesting because it lets us break down an integral over a long interval from a to b, and recognize that we can build that out of two separate pieces from a to some other value c, so long as then we restart at c and then do the integral the rest of the way up to b. So we see the same value in the upper end of one integral and the lower end of the next interval, then we can combine those two areas into one unified area, represented by one unified integral. Now, it's worth seeing some of these ideas laid out in proofs, and the textbook is an excellent resource for this. We're going to look at one of them and simply expand this or transform this into a sum form, and then see how that relates back to the integral formula here. But the starting point is simply recognizing that if we have the integral of, say, something like x squared minus e to the x, we can integrate the x squared first, and then we can integrate the e to the x and subtract them afterwards and get the same answer as the original. So clearing that off for a second and doing it in the general case, if we take the integral that we're given and recall the definition, so this is something worth remembering. Whenever we hit a new derivative and we weren't sure what to do, we would go back to the definition of the derivative, which we don't typically use day to day, but helps us to look at new scenarios. And the same thing would apply here. Remembering that, let's phrase it this way, the integral of f of x minus g of x is a sum. We're taking f of xi's, with little stars in them, minus g of xi, stars. In fact, actually, we'll take out the stars, and we'll make this the left-hand rule. So we'll do I minus 1 and I minus 1 times delta x. So remembering that these are our heights, and the delta x's are our widths, and then the sum that goes with that was from I equals 1 to n. But that's not exactly what an integral is. An integral is that sum of heights times widths when we add more and more intervals to the mix and let that number of intervals go to infinity. All right. Well, the nice thing about writing it as a sum is that we can focus on that part of the scenario, and we can use the operations on sums, if I add up f minus g at all these different points, I could get exactly the same thing. I'm just copying the limit down from before, but I would get exactly the same thing if I added up all the f values first times delta x's, and then I subtracted what happens if we add up all the g's, again times delta x's. So this is just like saying, if we add up these differences over and over and over again, I would get the same total if I added up the f values first and then did all the subtractions at the end and get the same grand total. Well, the nice thing about this is we can take this limit that we have and apply it to both of these sums. That would look like this. Sum from I equals 1 to n of the f values, and all of that minus the limit as n goes to infinity, the sum of the g values times delta x. And then we realize very quickly, now we have simple heights times widths, another height times width included with the limit as n goes to infinity. That's exactly what we mean by an integral. And so we'd have the integral of our function with respect to x. We didn't belabor the delta x and xi formulas because we're just getting back to the same integral again. But here we go. This limit here would be adding up heights and widths of the g function over an infinite number of intervals, or seeing what happens when we make the number of intervals larger and larger. Well, that's exactly what we mean by the integral of g of x. And so what we have is a replacement. We can take an integral, f minus g, and then separate it into an integral of f minus the integral of g, and it just relates back to the sum definition of each of those integrals. In this problem, we're looking at the same function each time, f of x, and what's changing here are the limits of integration. So 0 to 2, 1 to 4, and 0 to 4. And what we're going to try to use is one of the properties we focused on earlier, where we try to connect these intervals to find out a related integral. So let's sketch each of these out. So I'm going to draw 3 axes here, all lined up. And this is not going to be a detailed sketch for the function itself, but we do have is areas, or we can represent these as areas. For instance, the integral from 0 to 2 of our function would give an area of 3. The function doesn't necessarily need to look like this. It's simply enough to know that the area underneath it would have a value of 3. Meanwhile, the integral of the same function, so we had this function go on, if we do that same function from 1 to 4, we get an area of 2. So this isn't to scale, but that'll be okay. And then we put them all together from 0 to 4, we get an area of 4. And the question that we're being asked is, what's the integral from 1 to 2? So combining all of those, going back to the original function, what is the area under this function on this short interval from 1 to 2? So we'll answer this question in 2 different ways, one using intuition, and then one being more formulaic based using these properties. So if we're looking for the integral from 1 to 2, well, that's part of the interval from 1 to 4. But, well, we also know 0 to 4. We have to somehow put all these puzzle pieces together. I think, though, if we look at the comparison between 0 and 4 and 1 and 4, we can take one minus the other and figure out the interval from 0 to 1. If it's 4 for this whole interval, but 2 from 1 to 4, then there also must be 2 on this first interval, because these two together, when we add them, have to add up to 4. Well, it gives us as an ingredient then to go back in here. I'm just going to do this in color here. If we split this in half, we now know that there's 2 as the integral from 0 to 1, but we were told this whole integral was 3, and so there's going to be 1 left over there, and so we can actually deduce that the integral of this function, f of x, on the interval from 1 to 2 is going to be 1. Now, how can we be a little more precise about that? Well, if we just work through a bit of what we did earlier, then we can say the integral from, let's do this in blue, the integral from 0 to 4, let's go to 0 to 1. 0 to 1 plus the integral from 1 to 4. And I'm going to skip the f of x dx and f of x dx here because that's common to all these terms. And I just want to focus on the limits here. That is equal to the integral from 0 to 4. And we actually have values for each of those. So that was a 4. This was 2. And so the integral from 0 to 1 had to be equal to 4 minus 2, which is 2. So we're using this definition up here, or this property of integrals up here, to simplify that limit of integration. And then we can do the same thing again. The integral from 0 to 1 plus the integral from 1 to 2 is the same as the integral from 0 to 2. Again, keeping an eye on the corner limits here. If we're going from 0 to 1 and then 1 to 4, it's the same thing as going all the way from 0 to 4 in one step. Same thing here from 0 to 2. And then we fill in the blanks that we know. We were told the 0 to 2 integral was 3. We found the integral from 0 to 1 was 2. And then there's our missing interval there. So our integral from 1 to 2 of f of x dx is 3 minus 2, or 1. So we can get this solution in an alternative way as well.